I'm Steve Burgess. It's my pleasure and privilege to have served the last 2 years as president of the hydrology section of the American Geophysical Union. And the occasion we're gathered for today is the 1996 Langbein Lecture. And the first up, the Walter B. Langbein Lecture is the named lecture of the hydrology section of the American Geophysical Union. And I want to emphasize that the American Geophysical Union is us. It is not an organization. It is made up of us, and it can only be as good as us, and we must never forget that. The lectureship is awarded for lifetime contributions to the basic science of hydrology and/or unselfish service promoting cooperation in hydrologic science. We're assembled to honor the memory of the late Walter Langbein, as well as to accord recognition to our lecturer, a colleague of the first rank. The fourth Langbein Lecture will be given by Dr. Shlomo Neuman, Regents Professor, Department of Hydrology and Water Resources, University of Arizona. The title of his lecture is Uncertainty, Non-Locality, and Scale in Subsurface Hydrology, Current Concepts and Challenges for the Future. Before I say a little more about Shlomo, I want to say a little bit about Walter Langbein and a few other features that come into play. And I will read from you a vignette from the book Opportunities in the Hydrological Sciences, published by the National Academy of Press in 1991. This book is essential reading to all who are new to the field and those of us who have been around a little longer. It is known as the Blue Book or as the Eagleson Committee Report. This 348-page book, followed by almost 30 years, the 1962 report of the ad hoc panel on hydrology of the U.S. Federal Council of Science and Technology. That panel was chaired by Walter Langbein. One of the outcomes of the work of his committee was establishment of the interdisciplinary journal, Water Resources Research, first issued in 1965 with Walter Langbein and resource economist Alan Canesa, the founding editors. The first paper in volume 1 of this interdisciplinary journal was by now Nobel laureate Ken Arrow, entitled Criteria for Social Investment. The second paper was by Doug James, who's serving us so admirably at the National Science Foundation, entitled Non-Structural Measures for Flood Control. The 13 papers in volume 1 reflect the rich diversity of the field and Walter's vision of what can be published in a truly interdisciplinary journal. The vignette that I'll read is from page 44 of the particular book. And this is what it has to say. This was prepared by Nick Metalis, who knew Walter very, very well, and it just is entitled Walter B. Langbein, 1907 to 1982. In his long and distinguished career, Walter B. Langbein never failed to direct his scientific endeavors to the public good. He was indeed a scientific public servant. Langbein was born in Newark, New Jersey on October 17, 1907. While attending evening classes at Cooper Union, he worked with a construction company in New York City. He received his Bachelor of Science degree in civil engineering in 1931, and he remained with the company until 1935, when he took a position as hydraulic engineer with the U.S. Geological Survey in Albany, New York. Walter's sole academic credential was a Bachelor of Science degree in civil engineering. Langbein's interest ran the full gamut of hydrology. He was recognized in the scientific community as among the world's most versatile, competent, and distinguished hydrologists. He was an innovator and leader in a diverse list of hydrologic subjects: floods and flood hydrology, unit hydrograph studies, soil temperature, lake and river sedimentation, closed lakes, evaporation, reservoir storage, river meanders, the hydraulic geometry of river channels, base level and physiography, and the theory of kinematic waves applied to riverbed form. His studies of flood frequency, translated to indicate flood risk, became the basis of the 1968 National Flood Insurance Act. He contributed significantly to our understanding of the role of land use in conjunction with climate in the evolution of river morphology in time and space. Through his participation in programs of the International Hydrologic Decade, 1965 to 1974, which he was instrumental in founding, Langbein focused attention on the problem of determining the worth of hydrologic data relative to water resources development, thereby pointing the way to rational design of hydrologic data collection systems. For his scientific endeavors, pursued so cooperatively, Langbein was awarded the Bowie and Horton Medals of the American Geophysical Union and the J.C. Stevens Award of the American Society of Civil Engineers, the Distinguished Service Award of the U.S. Department of the Interior, and the prestigious Warren Prize of the National Academy of Sciences. He and Professor Korzen of the Soviet Union were co-recipients of the International Prize in Hydrology awarded by the International Association of Hydrological Sciences. Langbein took his work seriously, yet possessed a dry sense of humor. He once remarked that one's professional career is a race against obsolescence. Any hydrologic judge would claim that Walter B. Langbein clearly won the race. I've been aware of Shlomo Neumann's work since my graduate school days and first met him in the mid-1970s. We almost became colleagues in the same department. Stan Davis had been appointed the new chairman of the Department of Hydrology and Water Resources at the University of Arizona and was to start his duties in academic year 1975. He and colleagues had hired Shlomo to start at the same time. I interviewed for position in February 1975, and Stan came to Tucson for the interview. The prospect of working with such a group was extremely appealing, but the green beauty of the Pacific Northwest won out over the beauty of the desert, and Sylvia and I elected to stay in Seattle. Dr. Neumann received his BS in geology in 1963 from Hebrew University in Jerusalem. He received his MS in engineering science in 1966 and his PhD in engineering science in 1968 from the University of California at Berkeley. From 1968 to 1970, he was an acting assistant professor in the Department of Civil Engineering at UC Berkeley. He returned to Israel, and from 1970 to 1974, he was senior scientist and associate research professor at the Institute for Soil and Water, Agricultural Research Organization, Bet Dagan, Israel. He returned to the US in 1974, again to the University of California at Berkeley, and he moved to the University of Arizona in 1975 as a professor in the Department of Hydrology and Water Resources. In 1988, he was appointed to a distinguished Regents Professor position in his home institution, the University of Arizona. He's been honored in many ways. He received the Hydrology Section's Horton Award in 1969. He received the O.E. Meinzer Award from the Geological Society of America in 1976. He was elected a Fellow of the American Geophysical Union in 1984. In 1988, he was awarded the M. King Hubbard Science Award by the Association of Groundwater Scientists and Engineers. In 1990, he was honored by the American Institute of Hydrology with the C.B. Tice Award. In 1992, he was elected a member of the United States Academy of Engineering. Shlomo has been a distinguished lecturer on many occasions. These include the Birdsall Dreiss Distinguished Lecturer of the Geological Society of America in 1986 and 87, and the Distinguished Sherrard Lecturer at the University of California, Berkeley Geotechnical Society in 1994. He has served the profession well. He served between 1977 and 1984 as a member of the editorial advisory board of the Journal of Hydrology. From 1987 to 1993, he was an associate editor of the Journal of Water Resources Research. Since 1992, he's been a member of the editorial advisory board of Stochastic Hydrology and Hydraulics. He's chaired the Horton Award Committee, American Geophysical Union, has served as a member of the Hydrology Section Fellows Nominating Committee. He's given generously of his time to the National Research Council. From 1993 to 1994, he served on the Geotechnical Board, and 1994 to 95 on the Board of Energy and Environmental Systems. His research interests are many and varied, and to give the flavor of some of Shlomo's work over the years, I mention several of his papers or sets of papers. I think one that caught our interest very early in the game was with Paul Witherspoon, applicability of current theories of flow in leaky aquifers in water resources research in 1969. A paper that was really extraordinarily influential, his 1972 paper, Theory of Flow in Unconfined Aquifers Considering Delayed Response to Water Table. Something that captured very much the engineering community, extraordinarily influential in design. Saturated, unsaturated seepage by finite elements, Journal of the Hydraulics Division of the American Society of Civil Engineers in 1973. He turned his attention to inverse problems, and in 1979, with Sid Yakowitz, wrote the first of three-part paper, A Statistical Approach to the Inverse Problem of Aquifer Hydrology. Part one was theory, and in true Shlo fashion, there was a part two with a case study, followed with a part three, improved solution method, and added perspective in 1980. A later paper in 1984, The Role of Geostatistics in Subsurface Hydrology. And a more recent paper that give a sense of the flavor and diversity of this distinguished colleague. The Fractal Nature of Permeability and the Scaling of Effective Flow and Transport Parameters was published in 1995. It's my pleasure to introduce our distinguished colleague, Professor Shlomo Neuman, and to ask him to present the fourth Langbein lecture, the Hydrology section of the American Geophysical Union.
I'm grateful to my AGU colleagues for the honor of being named the 1996 Walter B. Langbein Lecturer. Though I have not been fortunate enough to know Walter Langbein in person, I'm well aware of his legacy, and I consider it a privilege to have my name associated with his through this lecture. I can only hope that Walter would have approved of my message. As this is the first Langbein lecture that is being delivered by a subsurface hydrologist, I thought that perhaps a few words of introduction may be in order. It wasn't so long ago that groundwater hydrology had amounted to not much more than sophisticated competition with dowsers. Like them, our major role was to locate reliable sources of subsurface waters and to maximize well yield. The competition was keen. Witness the number of semi-serious publications devoted to dowsing by scientific organizations, including the US Geological Survey. The last 3 decades have seen our rapid emergence from the relative obscurity of a decidedly low-tech profession to the forefront of activities related to humanity's rapidly growing concerns with energy and the environment. For a brief instance, the public has placed its trust in the ability of science and technology to help alleviate such concerns, and we have found ourselves in the limelight of this fleeting trust and hope. We have been faced and charged with problems of ever-increasing importance and complexity that included the need to improve water management practices by methods such as conjunctive use and artificial recharge, to foretell and forestall the consequences of groundwater withdrawal on land subsidence and on the onset of earthquakes, to store thermal, fossil, pneumatic energy underground and to utilize it efficiently, to dispose of hazardous liquid waste, e.g. boreholes, to characterize and remediate subsurface contamination, and to cite and assess the safety of nuclear waste storage facilities in geologic media. We have met these charges and challenges with great enthusiasm and confidence. Our exuberance had as much to do with the opportunity to engage in exciting science and engineering as it had to do with the prospects of attracting unprecedented amounts of funding from government and industry to our universities, laboratories, and consulting firms. Our confidence derived in large measure from a growing belief that subsurface hydrology rests on sufficiently firm and sound scientific principles to allow constructing reliable forecasting tools based on these principles in the computer. Much, if not all, that remained necessary for success was the further development of such tools and the application of sound engineering practices to the tasks at hand, or so it seemed. In the last few years, public support for science and technology in general, and our enterprise in particular, has ebbed measurably due to circumstances to which we have partly contributed. It appears that we have been overconfident in the powers of hydrologic and environmental science to address major issues of public concern. In particular, our perceived ability to help remediate subsurface contamination to regulatory standards under reasonable budgetary and time constraints has, I think, been exaggerated and oversold, as has our perceived ability to render believable hydrologic forecasts for purposes such as assessing the long-term safety of high-level nuclear waste repositories. How did this happen? In my lecture, I hope to touch briefly on this question. I will then suggest a conceptual framework within which I hope one should be able to render hydrologic forecasts without overstating their credibility, while remaining fully cognizant of their power and potential utility. Though my lecture focuses on subsurface hydrology, it has, I think, direct relevance to the current quest for improved understanding of the Earth's soil, vegetation, atmosphere system and its association with climate. I see three reasons why this may be so. One, there seem to be strong parallels between the exuberant confidence with which subsurface hydrologists have been meeting their challenges during the last 30 years and that with which surface hydrologists and atmospheric scientists are presently approaching issues of past and future climate change. Two, more directly, soil moisture, which is so closely linked to climate, depends strongly on subsurface hydrologic processes within and below the vadal zone. And last, the simulation of soil moisture and related surface or near-surface hydrologic processes is often done in manners similar to those employed by soil physicists and subsurface hydrologists. It is particularly common to represent soil water movement on both local and basin scales using Richard's equation, reflecting their premise that processes, if not necessarily their controlling parameters, operate essentially unchanged on a wide range of hydrologic space-time scales. My lecture addresses itself to the validity of this premise and related issues. Thank you very much. Now that I've been fully wired, we can start with the actual lecture, which is entitled Uncertainty, Non-Locality, and Scale in Subsurface Hydrology, three seemingly abstract, obscure, and to many, I'm sure, irrelevant terms. What I hope to do within this 1 hour is to show that, in fact, they are relevant, they are related, and that they pose, rather than answer, many interesting questions, which should give us plenty to do in the years to come. Subsurface hydrology has been deeply rooted in the tradition of classical fluid mechanics and the theory of flow through porous media. And in particular, it is based on partial differential equations, which are generally taken to represent fundamental physical principles, primarily of mass, momentum, and energy conservation, as well as constitutive laws that can be repeatedly tested in the laboratory. And what this implies is that the parameters which enter into these equations, permeability, porosity, dispersivity, can therefore be viewed as well-defined local material properties, which in turn can be determined in more or less unique manners in the laboratory and even in the field. Well, we know very well that flow-through porous media theory very often works quite well on the laboratory scale, but things become a little bit more questionable when we move from the laboratory to the field scale, and especially as the field scale enlarges. And the question is, why is this so? Well, my lecture will focus to some extent on precisely this question: why have our models not done as well as the theory would suggest that they should? But let me start by saying that most groundwater hydrologists, when asked, would probably qualify themselves as being determinist. And that determinism rests very, very strongly on these premises up here. There has been a tendency to develop models based on partial differential equations, to build into those models parameters measured in the laboratory on small scale, field scale, and to use those to generate forecasts on large scales in the field. I believe that we have been overconfident in the predictive powers of these models, both flow and transport. I believe that the premise that our science rests on well-defined principles of the kind I have just mentioned has given us overconfidence in the power to collect information on a small scale and through a reductive process upscale those into the field scale. How well has this worked? Sometimes well, sometimes not so well. We have found that our models deteriorate as far as their predictive or forecasting ability is concerned as we move from the laboratory to the field scale, from the local to the regional scale, from short-term to long-term. We have found that we can do much better in predicting and simulating steady-state groundwater flow than we are able to simulate and predict transient flow. We can do much better with linear than with nonlinear equations. Our forecasts are much more believable when they deal with flow than with transport, and they are much better when they deal with inert than with reactive transport. It is always possible to make our models work because we build into them a large number of parameters with which we can play and adjust so as to fit observed behavior. We have been doing not as well when it came to using these models to predict conditions other than those under which they were calibrated. The only way in which these models can be kept doing the job continuously is by recalibrating them again and again and again. Now, it is believed today by many that one major reason why this is so is uncertainty about the geologic system within which these equations are applied. And what I would hope to do today, within the short time allotted to me, is something which is perhaps overambitious, and that is to suggest to you the framework of what I believe could serve as a unifying concept through which we could try to address the question of uncertainty and how it affects our ability to render predictions that are believable by quantifying that uncertainty, how we can perhaps attempt to reduce uncertainty through a reliable data collection process, how we can bridge across scales, and how we can bridge across flow and transport regimes. We are finding ourselves, I think, in a rather unique and interesting situation where the laboratory-determined physics of flow through porous media is relatively simple. There is still much to be learned. Nevertheless, the basic processes on the laboratory scale, certainly for saturated flow, steady and transient, even linear and nonlinear, are pretty well understood, and they are relatively simple. Where the complexity comes in is in the geology. We deal with a very complex geologic system which exhibits variabilities on many scales, both discrete and continuous. We have small-scale fractures, dikes, folds, bedding planes. Within a single bed, there are variabilities that very often can be described in a continuous manner. The question where to make a distinction between discrete and continuous representation is not very clear. And the parameters that enter into our partial differential equations therefore can be expected to do likewise. These parameters can be measured only at selected well locations within selected depth intervals in these wells. They depend on scale and the support volume as well as the mode of measurement. Let me illustrate the dependence of permeabilities as determined in a deep borehole in fractured granites in Sweden on the scale of the distance between two packers that are used for the establishment of these numbers. In a borehole in fractured granite that goes down to 300-something meters, the large bars here indicate 20-meter scale measurements. These indicate 2-meter scale measurements. And we can see, of course, that there is not only a much higher frequency, but a very different amplitude and distribution to these parameters. At the same time, the measurements depend on the mode of measurement, or the values that we determine in the field or in the laboratory could vary greatly. This is an example of contoured values of permeability at the Las Cruces train site in New Mexico, and I think that the picture speaks for itself. So they depend on the scale, or what I will refer to as the support volume of measurement, and on the mode, which includes instrumentation, procedure of measurement. One could perhaps suggest that in the case of permeabilities such as these, one should be able to upscale and downscale these permeabilities through linear convolution and deconvolution methods. And indeed, this works sometimes when flow is essentially parallel to the layers, but it does not work in general, and therefore is not a general panacea to the problem of scale dependence with support volume. And of course, the parameters suffer from random measurement, interpretive interpolation, and sometimes averaging errors to the extent that we do averaging. So where does this take us? Well, first and foremost, once we recognize this very clearly, we should admit that in our models, based on partial differential equations, all the inputs, and I'm sorry, the word input is mentioned twice there, that's an error, into the flow and transport equations, which means primarily the parameters. Let's think of the logarithm of permeability as the parameter on which we will focus our discussion, though I'll be mentioning others as well, must be defined and measured on well-defined and consistent scale, and that must be the support scale if we want to relate our model to measurements. I'm going to assume that we have one well-defined support scale. We all know that in groundwater hydrology, our data are collected on a variety of supports. But for the sake of this discussion, bear with me, please, and just accept the concept of defining everything on one support scale. And if this is so, then clearly we must understand the outputs from our equations as being valid only on that same scale unless they were integrated in space and in time. But the standard results from the solution of a partial differential equation by finite differences and finite elements as an example, or by analytical methods, should be understood to provide you with information on the same scale. In subsurface hydrology, because of the fact that our data come from so many different support scales, are evaluated on so many different supports, we have been rather cavalier about the definition of both the input and the output scales. And of course, our inputs are random because of the uncertainties about what the parameters would be where measurements are unavailable. There is a random error associated with them. As a result of that, the outputs have to be understood to be random, which then immediately renders our flow and transport equations stochastic. And the question that I would like to address, among others today, is what does this imply about our traditional deterministic models, the ones that most of us still use in our everyday practice, both in science and in engineering? Now, the approach that groundwater hydrologists have taken over the last 20 or so years rests very firmly on the geostatistical philosophy with which most of you are well familiar, I'm sure. According to this philosophy, one views the measured parameters of a given kind, say permeability, in a distinct hydrogeologic units. And the question, what is a distinct hydrogeologic unit, does not have a unique answer. One would, on the basis of the best geological, geophysical information available to him, make some kind of a discrete separation between lithologic units that bear the hope of having some degree of internal homogeneity. And it is to such units that the concept should be applied. But because it is so difficult to delineate these boundaries, it is not always so applied in practice. But within such a quasi-homogeneous units, the geostatistician would view measured parameters as a sample from a random field. For example, in the particular units that I'm showing you here, one encounters both sandy and dolomitic types of facies. Core data collected at various locations within boreholes of one of these units would yield porosity values, which when put together into one bag might show a frequency distribution such as this. And this, of course, is a frequency distribution based on data collected spatially over a large volume of rock. To the geostatistician, it would be valid to take this distribution and claim that, in fact, at every single location within the rock volume, the permeability, or in this case, the porosity, is random with this kind of a distribution. This process of taking spatial data and projecting them onto one point, assuming that at that point the variable can change from one value to another, not in real space but in probability space, we sometimes call ergodicity. And the term will come up again. So through this process then, our field, our permeability field, is characterized by a probability density function, joint because we have values that vary at different points and there is a joint dependence among them. And associated with these are moments, which we will term ensemble moments to distinguish them from spatial moments. Moments in probability space as opposed to in real space, such as the mean and the variance and the spatial autocorrelation, which we very often show through a correlogram or a variogram. The fields are allowed to be cross-correlated. For example, here we have a rather nice cross-correlation, very simple regression type on a scattergram of permeabilities with porosities, both in the sandy facies and in the dolomitic facies. It doesn't always work so well, but when it does, it certainly helps the analysis. It works a little bit less well, and I've looked for the best example that I could come up with when one tries to cross-correlate permeabilities with some type of indicator of fracturing, most notably fracture density. Usually the correlation is much worse than what you see here. And I'll be coming back to this question of how to distinguish between porous and fractured rocks very briefly a little bit later. So all of this can be taken into account in the geostatistical conceptual framework. And then one can proceed to do something with these data. Once the statistics, mean variance, autocovariance, and so on, have been determined based on a discrete sample, one can then either conditionally or unconditionally project the information away from the points of measurement, both through stochastic interpolation, sometimes going under the name of kriging, or through averaging, as well as through the generation of many possible equally likely realizations of the permeability field, because we don't really know what it is between the points of measurement. So anything that we project it to be between the points of measurement is either a best estimate, a smooth estimate, or a wiggly field around that estimate, which comes a little bit closer to reality, but of which there is not one, but an infinite number of possibilities. Here is an example of an interpolated air permeability field in fractured rocks based on packetless data at the Apache Leap research site that we are operating north of Tucson, Arizona. And here is another example. This is in a vertical plane of the same map. And if you compare the two, you will see that they are very similar to each other. The difference being in the prediction of the uncertainty or the estimation variance associated with these maps when one uses different surmised or inferred correlograms or variograms for the underlying data. In this case, we assume that the variogram has a constant CIL of the kind I will show you in a moment. In this case, we are dealing with a fractal field represented by a variogram that is represented by a power law relationship. Please try to remember these. I'll come back to them later. But the power law variogram, you cannot read the numbers, suggests much lesser certainty in these estimates than does the standard variogram that you will see in most geostatistical analyses of the day. Now, if one accepts the philosophy that data can be interpreted within the geostatistical concept or context, then the next logical step is to proceed with the philosophy of stochastic flow and transport analysis, which takes this into the flow and transport prediction domain. In geostatistics, we interpolate data, we estimate their distribution between measurements. We can perhaps come close to generating real-looking plots of those data, but we do not say very much about the flow and the transport in fields such as those that we represent, that we obtain through the geostatistical process. Stochastic theory allows us, supposedly, to do so by taking the output from geostatistical analyses and generating through it solutions to our stochastic partial differential equations of flow and transport. One can either generate these conditionally or unconditionally, the difference being that the conditional analyses takes into account the known position of measurements in three-dimensional space, whereas unconditional analyses only take the general statistics of the field into account. The results could be dramatically different from each other. Here is an example of flow paths predicted using stochastic analysis of radionuclides that might be released from the WIP repository in New Mexico into the Culebra dolomite, which is one of the high permeability fractured rock units overlying that repository. And since there is great amount of uncertainty about the distribution of transmissivities within the Culebra dolomite, one cannot come up with a certain prediction of which way these radionuclides would travel. The red line here would be the prediction that one would obtain if one used average values of transmissivity, for example, such as those obtained from estimated through kriging values. And this is your distribution. If you take predictions, you can never eliminate the uncertainty, of course, but you can greatly reduce it by doing conditioning on data. And so much of my emphasis is going to be on predictions that are done through conditioning on data. Now, one can predict mean flow paths, like the red one that I have shown you, or one can generate these random distributions of flow paths and various other outputs from stochastic equations the way you see here. The question is, what do these mean predictions mean? Do they have any meaning whatsoever, given that even in the best of circumstances, there will still be this very large distribution around it? There's a big argument in the literature whether they are useful or not. Some would say that some would seek behind the mean predictions some relationship to the actual observable, in this case, flow paths. And if such relationship is not evident, one would perhaps start questioning the utility of this kind of an analysis. Another view of the conditional mean prediction would be to view it as a best smooth estimate of the actual non-smooth path, which we hope would be one of these, but we don't know which. And so therefore, I would suggest to you that it makes a lot of sense to look for these conditional means, not to look for a direct relationship one-to-one between them and reality, but to view them as the best prediction that one can make under uncertainty, and associate those also with the calculation of the prediction error variance, which we have just seen diminishes considerably with conditioning. There is this problem of geostatistical inference that may be fatal to the entire approach. And so do many people claim. And that is that, remember please, that the geostatistical philosophy views measurements in a single aquifer down there as belonging to a random field that varies in probability space. Everything is based on so-called ensemble statistics, which are defined not in real but in probability space. This is also what underlies the concept of stochastic prediction of flow and transport. Those stochastic predictions are done within the context of ensemble statistics in probability space, yet the data come from one single realization. And the question of inference is that of taking these data from a single aquifer and translating them into the language of geostatistics and stochastic modeling, which unfortunately requires some assumption of homogeneity and ergodicity. Ergodicity, again, is this ability to replace spatial averages, variances, with ensemble equivalents, and vice versa. Now, homogeneity can in fact be inferred from the data, but ergodicity cannot. And therefore, one has to live with this ergodicity as a hypothesis that cannot be directly tested, verified in the field. There are additional problems associated with the approach, such as the requirement that if all these data that you collect from a single aquifer and put into a single bag appear to be distributed normally, as an example, you would then assume that at every point that distribution is also normal, which would then render the entire field multivariate normal, and it simply is not possible with current data to test this hypothesis. So there are several of these hypotheses that are required, and the question that one could legitimately ask, and is being asked by our colleagues all the time: what do you do about this philosophical dilemma? Does it kill the entire approach? Some people would argue that it probably does. Well, if you recall my title, I've included in it a few challenges for the future. And so here I would like to start with two challenges for the adherents of geostatistical and stochastic theories and to those who reject this framework. To those who support it, and I obviously am one of those, I think that it is incumbent upon us to demonstrate more often than what we have done in the past, and certainly more convincingly than we might have been doing in the past, that it is consistent with observations, and this is the only way in which we can support it. Consistency with observations would indirectly support the underlying premises, including the premise of ergodicity, if and when it applies. Unfortunately, there haven't been enough of attempts to do so. For those who reject it, I would like to pose an even grander challenge, and that is that it would be incumbent upon them to supplant the geostatistical stochastic conceptual framework with an equally powerful alternative that is philosophically more satisfying. Some believe that this will be possible in the future through a greater introduction of geological, geochemical, geophysical data into geostatistical analysis, and it certainly bears hope. We know today that some flow and transport parameters, or states such as concentration head and so on, may show some cross-correlation with geological, geophysical, and geochemical signatures. It may be possible to reconstruct the geology. For example, the lithofacial distribution or the architecture of an aquifer in terms of mineralogy and rock properties, and cross-correlate that with petrophysical properties, which include flow and transport properties. Here's an example from the same aquifer that I was showing you before, where geostatistics has been used to map out between the boundaries that I showed you earlier, between the discrete boundaries, detailed distributions of the dolomitic and sandy facies within the aquifer, and then statistically ascribe porosity and permeability to each one of those facies. More of this kind of work, I'm sure, will be coming, and it bears considerable promise for the future. Furthermore, one can attempt to bring in structural geology, attempting to reconstruct discrete features, such as faults, dikes, fractures, and so on, and relate those to flow and transport characteristics. But here I would like to sound a note of caution. In recent years, there have been quite a few attempts to do precisely this, and to do it in what I would call the par excellence example of reductionism, whereby in order to generate material properties for typically finite difference, finite element models of flow in an aquifer, one would, as a first step, make a tremendous effort of mapping out in detail on the surface, in underground openings, within boreholes, all the details of fractures on all scales that would show on these openings and within these boreholes. And then usually through some kind of a statistical projection process, which is other than standard geostatistics, because this is now discontinuous features, would generate thousands and thousands of these fractures, develop a computer model through which water would be forced, and then use the output of this computer model to predict what the large-scale block permeability, porosity, and so on of the rock would be. There isn't even an attempt to apply this kind of an approach to Yucca Mountain in Nevada. And I am firmly convinced that this kind of an approach has not yet proven itself. I don't know whether or not it has a future, but I don't think that it has a viable present. I think that more parsimonious models so far, if applied with the same amount of fervor and funding to these problems, could show equally, if not more, reliable as models, as forecasting tools for these sites. So a challenge is, of course, to further develop these kinds of data augmentation methods to help reduce uncertainty about subsurface flow and transport. A grand challenge for the distant future, though it started already with some attempts these days, is to bring in not only static relationships between geologic features and flow and transport behaving, controlling parameters, but also dynamics into the picture. And I think this is really an open and extremely exciting possibility for the future. There are very few examples that appeared in the literature, one of them being a recent paper by Steve Gorelick and Chris Coulterman from Stanford in Science 2 years ago, I believe. A major challenge is to directly and indirectly verify flow and transport predictions based on such reconstructions against independent field observations, something that groundwater hydrologists would like to do, but unfortunately not always have the funding and the time to do. A little bit more on homogeneity and ergodicity. I mentioned variograms. There are many who believe that in fractured rocks, since variograms are based on the geostatistical philosophy of a continuum, that in fractured rocks they do not apply. Here is a very nice example of variograms developed at the Stripa mine in Sweden in fractured granites based on Packer-tested permeability data. These are classical. They are the best that you can think of. There are many examples of this. The only thing you need is to have enough data to show this kind of behavior. For those of you who are not familiar with variograms, Let me just very quickly mention to you that essentially they are inverted parallelograms. The smaller the value, the greater the statistical relationship between any two sets of data, any pair of data separated by a given distance. Therefore, the smaller the value of the variogram, the greater the predictability from a measuring point away from it. This is called the sill of the variogram, and it is equivalent to the variance. If it flattens, one can take that to be an indication of statistical homogeneity. The distance at which it tends to flatten is a measure of correlation scale. This is the second scale I'm bringing into the picture. The first one was the support scale. Now comes the correlation scale, the spatial correlation scale. So under homogeneity, there is a unique variance or sill and a unique range or integral scale, a measure of spatial correlation. And as I said, this is, and I think can very often be taken as an indication of statistical homogeneity. Now, most stochastic flow and transport analyses are based on this kind of a homogeneity assumption. And this homogeneity implies that under special conditions, such as mean uniform flow, like your classical Darcy experiment in the laboratory in one direction, in an infinite domain, if you exclude boundaries from consideration, flow becomes Darcian on the average, on a scale much larger than this integral scale. That brings into the picture the representative elementary volume concept, which is so embedded in our thinking process. The transport becomes Fickian in the mean, but it is recognized today that a plume has to travel a certain distance before the dispersivity becomes a constant. Changes with travel distance of a plume and may become a constant. The transverse value may or may not become a constant, but the longitudinal value we know becomes a constant if you only wait long enough. And that's where the classical Fickian theory becomes applicable. Under homogeneity, dispersivity is already scale dependent, because contrary to the laboratory conclusion that it is always a constant, always Fickian, it grows with distance at a one-to-one rate under homogeneity. Now we are finding in recent years that this concept of homogeneity is not always supported by the data. Although variograms do very often appear to flatten in the way I have just shown you. And indeed, it is then possible to extract from each such flattened variogram a single variance, and more importantly perhaps, a single correlation scale. When one collects these correlation scales obtained in various hydrogeologic units worldwide by that homogeneous inference method and plots them as Lynn Gelhar has done in his book versus the size of the field within which data were collected. If you wish, the window on the aquifer that was sampled, those seemingly constant values of correlation scale lambda increase indefinitely with the size of the window. So here is another scale of interest. How large is the window within which you are sampling? The correlation scale appears to be almost consistently 1/10 of that window, because the slope of this line is 1-to-1, but there is an offset in the ordinate versus the abscissa. Why is this happening? Furthermore, in some locations, such as our own Apache Leap research site, which is a small block of rock, 35 by 35 by 35 meters in unsaturated fractured tuffs. If one measures permeability using air in the system and plots the variogram not in the standard way on arithmetic paper but on log-log paper, one finds that it is possible to fit the data with a straight line. This is on a small scale. And if one does this for transmissivities in an aquifer on a scale of up to 100 kilometers, one finds that at least above a certain range, if one simply forgets this one point down here, the rest of the data can also be fitted by a straight line. Now, this straight line suggests that the logarithm of hydraulic conductivity, which I will call y, the natural log, rather than being representative of a homogeneous field, is in fact representative of a random fractal, a non-homogeneous field, which nevertheless may have homogeneous increments. And I've already shown you before the consequences of making predictions of error, estimation error, interpolation, extrapolation error, using the stationary model and using this power law or fractal type model. Fundamental difference. It appears, therefore, to me that stationarity, as derived from data by indicators such as the flattening of a variogram, may in fact be an artifact. It may be an artifact of the scale of observation, as we have just seen, the field size, and it may be an artifact of the method of inference. Such a simple thing as plotting your variogram on log-log versus on arithmetic paper. If one juxtaposes hydraulic and tracer data from many sites, then one finds not only this very interesting 1:10 ratio between the apparent correlation scale and the scale of the window, the size of the window, but one also finds that the variance, in this case we are plotting variance multiplied by correlation scale lambda versus lambda, that it also varies consistently, and furthermore, that these lines can be predicted independently of these data. In fact, I've predicted these lines based entirely on my 1990 interpretation of tracer data. These are permeability values, and I have predicted these lines on the basis of totally independent tracer data, which I'm going to show you in a moment, but you have seen those graphs many times before. So it appears, if you accept any of this, that there is some kind of beautiful simplicity to the complexity of geology, at least as manifested through these kinds of parameters. And if this is so, then I think we are posing a really interesting grand challenge to address the profound question, how does the natural subsurface environment evolve toward such a high level of what appears to be self-organization? We haven't even started touching that question because we are still debating whether or not it is so self-organized, which is, of course, valid at this stage of the science. Now, assume that it is indeed legitimate to view permeability as a fractal or multi-scale, multi-correlation, because it no longer has a single correlation scale associated with its field. What does that imply with respect to flow and transport? Can that explain the observation that permeabilities seem to increase in a consistent manner with the scale of observation? Can this explain the highly debated, hotly debated, apparent increase of dispersivity, longitudinal dispersivity, with the scale of observation, or with the mean travel distance of a plume? We are starting to develop theories which, in fact, make this link theoretically, and therefore support the possibility that there is a direct relationship between these kinds of observations and the multiscale behavior of permeability fields. In fact, we are about to send to George Hornberger, whom I saw before here somewhere, a paper that will precisely predict the effect of domain size that I just showed you a moment ago on the apparent increase in variance and integral scale of the log hydraulic conductivity with distance. And we think we can also predict the supralinear, because remember, dispersivity under homogeneity assumptions varies linearly with distance before it flattens. That is a homogeneous phenomenon. But this graph shows supralinear, higher than linear rate of increase. And that, too, we think, is possible to predict theoretically based on the assumption that the underlying permeability field has this power law diagram, this multi-scale behavior, this random fractal nature. And so here there's a major challenge, of course, if you believe in all of this, is to continue developing more powerful, more general stochastic theories and models for multi-scale random media, which will be backed by observations. Because we can develop these models ad infinitum, they mean nothing unless we have data to support them. A few words on routine stochastic models of flow and transport. Their purpose, of course, is obvious. It is to predict and simulate future and observed behavior under uncertainty. And the methods that we have been employing today are analytical, but much more commonly numerical. As much as I love the analytical technique because it provides you a tremendous amount of insight that the numerical methods seldom do, there's an advantage to the numerical method in that it is much more site-specific. You can address with it very complex problems. And the method is called Monte Carlo simulation. If you condition it on the data, it's called conditional Monte Carlo simulation. And of course, it is very simple, both conceptually and in terms of actual use. All you need to do is adopt your standard partial differential equations, the ones with which we started. But adopt them on the support scale of your data. Remember, we are assuming that all data are defined on one support scale. It could be a core scale. This methodology I'm talking about right now would require that you develop your numerical grid, finite difference grid, finite element grid, on that support scale. And then solve your equation, generate random, equally likely possible distributions of your permeability field, and for each one, solve these partial differential equations, and then either average the results or look at individual solutions or realizations, which are equally likely, therefore differ from each other. And I would like to suggest that, in fact, we should be striving, if at all possible, toward a calculation of a conditional mean and viewing that conditional mean as an optimum, unbiased minimum variance, predictor of actual behavior, not as a replacement for actual behavior, not as a true predictor of the actual behavior, but as the best that we can do under the circumstances. And view the second moment, variance, covariance, of these calculations as a measure of the prediction error. And this is critical for what I'm going to say next, because Monte Carlo methods are very powerful, but they are numerical methods, and as such, they have quite a few problems associated with that. But before we go into that, let us just look at one example, again, of a simulation of flow and transport, transmissivities and velocities and breakthrough curves at the Culebra Dolomite whip site in New Mexico. This particular work was done by Peter Gringrod and MP. We see here a smoothed estimate of transmissivities in the 8-meter thick fractured Culebra Dolomite. So this would be your mean estimate of the transmissivity with relatively smooth contours. If one uses a power law variogram, if they have done, one can then conditionally generate equally likely transmissivity fields which are much less smooth, much more grainy than this Krieg smooth estimate. And since they are all equally likely, even though they are all equally likely, they may be very different from each other, and I've selected two that look quite different from each other. One generates high permeability channels through the system. The other one does so to a lesser extent. As a result of that, the velocity has a tendency to be very high along these channels in one case, and much less so in the other case. And as a result of that, the concentration breakthrough curve that would be calculated based on this realization, which is equally likely to this realization, is fundamentally different. One might not know this if one would not formally take this uncertainty into account. And all of this was done by standard Monte Carlo method. So Monte Carlo methods are extremely powerful. Where do we stand with Monte Carlo methods? One of the difficulties is that they are computationally very demanding, and so we are not going to see them used in practice very often unless one has large amounts of funds and time to play with them. The reason they are so costly is because, as I have mentioned earlier, to do it right, you have to take your grid size on the scale of your support of the data. It is not always done so, and I'll be saying a few words about that in a moment. And of course, because we are interested in a mean, you need a large sample to obtain meaningful mean and variance, so we need to run this many, many times. In addition to that, there are some real problems with making sure that the Monte Carlo method solution has in fact converged to its theoretical result, which we can never verify. Grand challenge to those of us who are numerically inclined, of course, is to continue developing accurate and efficient computational tools to conduct these high-resolution Monte Carlo simulations, and hopefully, but this is probably work for mathematicians, to derive reliable criteria by which to ascertain the quality of their results. But until and unless this will be achieved, we are probably going to remain interested in pursuing more traditional methods. This then brings us to the issue of equivalence and upscaling, which I've mentioned very early in my talk, the upscaling part, not the equivalence part. It can be shown rigorously that if you make the best estimate possible of what the permeability distribution in an aquifer is, surely. Thank you very much. You're welcome. That's why I couldn't hear myself. Appreciate it. That if you make the best possible estimate of what is down there and plug it into your deterministic flow and transport prediction model, it can be shown rigorously that what you get is a biased prediction. What you want to plug into this model is something else than the best estimate of what is down there, because remember, you're plugging in an estimate of what is down there on the scale of the support. Now, it is possible to reduce this bias with standard equations, but it is unfortunately not possible to completely eliminate it with standard partial differential equations. You can reduce the bias by replacing your best estimate of what is down there with so-called equivalent or effective parameters, a term we all are familiar with. This is usually done through a process called upscaling, and it means different things to different people. But the standard process of upscaling is beautifully illustrated in this recent PhD dissertation from Stanford, which shows a support scale 1,000 by 1,000 pixel map of a piece of rock with its distribution of permeabilities on a grayscale, and a process whereby that grid is coarsened to a 20 by 20 pixel map through a very simple calculation. You take the fine grid, replace it with a coarse block, and then you apply flow in one direction, and you calculate the resultant, you apply a head gradient, you calculate the resultant flux, you get a K value. You do it in the other direction, you get another K value. And these will be your equivalent or effective block upscale permeabilities. There are more sophisticated, less sophisticated ways of doing so. But as I say, unfortunately, no matter how you do it, you will never eliminate the bias. And the reason you will never eliminate the bias is because upscaling of any kind whatsoever of random parameters, and we are treating our permeabilities as being random, will always yield uncertain equivalent values. But the biggest problem is that upscaling postulates the existence of a so-called local relationship between head gradients, as an example, and fluxes. Local means at a given point in the aquifer, you can tell the relationship between maybe block averaged gradient and block averaged flux locally. You don't need to go to the neighboring block to say anything about it. It can be shown theoretically that in fact those relationships are generally non-local. Meaning that what happens at this point in terms of flow will depend on what happens at that point in terms of gradient. And in addition to this, upscaling requires the a priori definition of a computational grid. How do you know how coarse you should make your grid for upscaling purposes? Wouldn't it be nice if you didn't have to do this a priori, but could perhaps do so a posteriori based on some knowledge of just how smooth or non-smooth your field is going to be? So I would like to propose to you precisely such an alternative. For lack of better terms, I will refer to it as conditional smoothing. I hope that I'll find a better term for it. You can view it as an alternative to both Monte Carlo simulation and upscaling. And its principles are illustrated on this slide. And I don't know if you will, Steve, allow me to go to an example, so I'll skip the mathematical example and not go into that. 5 minutes, I'll skip it. The idea is to develop flow and transport equations which are satisfied by these conditional mean ensemble and conditional ensemble variance, conditional moment. It turns out that these equations are not differential, but integral differential. And so if you approximate those integral differential or non-local equations by local standard partial differential equations, you get all kinds of mathematical problems. The main thing to understand is that they contain both local and non-local parameters which are conditional on the data. So if you work with these alternative equations, you discover not only that Darcy's law no longer holds and Fick's law no longer holds, but that you're now working with parameters which cannot be determined at a given location because they depend on more than one location. Furthermore, they cannot be determined uniquely because they depend on their data. And for lack of time, I will skip some of the graphs, but some of my overheads, simply to tell you that what this implies is that you should never be surprised if today you calibrated your standard finite difference model against one set of data, And tomorrow you collect more information, and lo and behold, you find it in the same aquifer. You suddenly have to completely recalibrate it and get completely new parameters. Of course you do, because your parameters are in fact an artifact of the data and the equations that you have fitted to the data. I had a few more overheads here, and I could go into the detail, but given the time, let me jump to the final slide or overhead that kind of summarizes the essence of what I just said. If these kinds of non-local equations can be developed, and we have so far developed them for saturated, meaning linear, steady state, and transient flow in porous medium. We are now working on extensions to more complex situations. But if they can, then they imply this with respect to our traditional models. They imply that traditional deterministic partial differential equations, when applied under uncertainty, which is almost always, except maybe in some special laboratory cases, are at best space-time localized versions, we may not know that, of rigorously correct, under the various assumptions that we have introduced through our talk, of non-local conditional mean flow transport equations. And since such a localization is not generally valid, it may be valid in some cases, neither are our standard deterministic PDE-based models, and they are biased. Treating local parameters as material properties, which is what we usually do, ignores both their non-local nature and their dependence on the data. It is not that the parameters are not material properties, it is only that we don't know what they are where we have not measured them, yet we are applying our equations there, and that is where the problem arises. If we sampled the entire aquifer and made it into Swiss cheese with no cheese at all, then and only then will we be allowed to do what we usually do. Hence, local parameter estimates are inherently non-unique, and we should never be surprised that they are such. We have expended a tremendous amount of time and energy in developing more unique ways of solving the so-called inverse problem. But the solution is non-unique not only because of the mathematical properties of the inverse problem, but it is non-unique because of these fundamental reasons. Like their conditional mean counterparts, these non-local equations, the standard deterministic partial differential equation models yield at best an estimate of what is down there. We sometimes tend to fool ourselves that they, being deterministic, give us something better than an estimate. Clearly they don't. The problem is they give us a biased estimate. Unlike the former, deterministic model predictions tend to be biased and non-optimal. And in addition to that, of course, they provide you no way of predicting just how well or poorly you are doing. And this is precisely one of the image problems that we have with our models being less believable than we thought that they might be. And this might be one of the reasons why Congress has shut off some of the funds for the Yucca Mountain project at the present time. And I'm not joking. There is a direct link between the two. So I think that we have come a full cycle seeing some reasons, which I think are quite fundamental, for why our models have not been doing as well as we thought they might, despite the fact that down on the laboratory scale, they appear to be based on rigorous fluid mechanics, rigorous physics, but the geology is complex. Thank you very much.